All right. Hello, everyone. Welcome to our course reading group for differential geometry. Starting from today, we're going to we saw like two very wonderful introduction of this course, and then we're going to start talking about some concrete topics of differential geometry. Today, we're going to start with a basic one, curves. So before I start, I actually have something I would like to say. I call it a preface. So basically, differential geometry may seem a bit disconnected from our ongoing research, especially when we are talking about things like more abstractly in the beginning, right? Like in today, we're going to ask questions like, what is a curve? However, in order for us to reach a fruitful destination, we actually need this kind of formalism. So we're going to start with very basic concepts. I hope you will enjoy the beauty of rigor along this way as I do, but just give you this preface to sort of saying we're going to look at some basic things. When I was preparing the slides, this actually reminds me my first time taking the real analysis course when I was undergrad. So you learn a lot, you learned for math for many years until calculus. Then after that, people started to ask very basic questions like, what are real numbers, right? Sorry, start from what are natural numbers, then move on to what are rational numbers, then what are real numbers. This kind of basic questions. I hated it for a while, but after several classes, I figured out the beauty of it. So I hope through today's discussion, you will feel the same way. Okay, that's enough of my opinion. So let's jump into the stuff we want to talk about today. The roadmap is like, we will first ask very basic questions of what is a curve. Then we are going to define a curve. And then, of course, in a differential geometry way, we're also going to define a so-called parameterized curve. And then based on this parameterized curve, we're going to discuss its invariance. And then we're going to come up with a canonical way to parameterize this curve based on the arc length of the curve. We are also going to see the coordinate invariance, basically in one frame called the Fermat frame. And then there are two nice theorems we can develop under this frame called the fundamental theorem of local theory of plane curves or of space curves. Finally, if we have time, I have some extra slides listed in the appendix. Those slides are just like some terminologies you might want to get familiar with. But if we don't get there, that's totally fine. You can just check the slides because I don't think that has any major influence of what we are talking about, the whole storyline. Okay, that's it. Let me get started. So our first question is a very basic one. We want to ask, what is a curve? Can you define a curve for me? So back to calculus, many of us are probably familiar with this, that we define a curve using a function, a parameterized function. Basically, what we are saying is that we have this function from R to R2, right? Right now, we're talking about is like 2D. So we define this function from R to R2, you probably use some parameter t and saying that, okay, for each t value, I'm going to map it to an xy coordinate in R2. Then by changing these t values, I can get basically the shape of this curve. Okay, this is the definition we used to see, but is there a problem of this definition? And then in differential geometry, how do we formalize it? So we see several subtleties actually make this function definition conflict with our intuition. The first subtlety is that geometrically, if we think about what is a curve, it should be like a curve, right? It shouldn't be just a single point. But if we take the function definition here, and then we just come up with this identity function by mapping any t just to 0, 0, then it perfectly satisfies the function definition, but it is not a curve anymore, right? It is just a single point. So in this case, we see that following the function definition, we do see some contradiction with our geometric intuition. The second subtlety here is Well, we can define a curve in this way, but the definition given by function won't be one-to-one. So let's look at this example here. The first R1 takes t, maps it to the xy coordinate t to t. So in this case, it just corresponds to this dashed line showing in the coordinate, right? This just y equals to 2x. This is a valid function definition of this curve. Well, I can come up with a different function, right? So when t less than equal to 1, it is the same as R1, t to t. But when t is greater than 1, then this function changes by the rate of change of its position regarding t has doubled, right? This time, when I change 1 unit of t, the value of x and y will change by 2 units. Although it still stays on the same line, but the function is a different one. So you can think of this as James driving a car on this line, but when he reaches this t equals 1, there is an accelerator. So he suddenly speed up, doubled his speed. So following both functions, we get the same curve, but this non-one-to-one mapping can really cause some trouble for us. So the third subtlety here is that when we are talking about functions and when we are talking about curves in the space, the terminology sometimes won't match. Let's see, what do I mean by this? So imagine I have this function RT, which equals t squared t cubed, right? I can plug in all the t values, and then I can draw this curve out, which looks like the green line on the left-hand side. In this case, this function t squared t cubed is perfectly smooth because I can take, by smooth here, we can think of it as infinitely differentiable, right? Both t squared and t cubed, I can just take any derivatives as I like. So we call it a smooth function. But instead, if we're looking at the curve on the plot at the point 0, 0, it's definitely not smooth. There is this cusp, right? So again, if we think of it as driving a car, for the upper half of this curve, you are driving the car very smoothly. But once you reach this original, what you do is that you in an infinitesimal amount of time, you turn your steer and then you directly change, you really quickly change your direction. So we cannot ask questions like, what is the derivative, right? What is the change of rate at this point? So this makes it no smooth. So with these 3 subtleties in mind, we see that a definition in terms of functions may not be the best way to define a curve. So we really need to have a new definition of curve. So for people doing differential geometry, they try to come up with a new definition in terms of geometry. So they say that, well, a very intuitive idea of saying what is curve is a set of points, right? But rather than just saying this is a set of points, we need some further properties of this curve. So this is what we're saying. Just to remind you, we're not saying it's a function, but we're saying it is a set of points. Then what kind of definition mathematicians gave precisely, right? They were saying that a curve is a set of points that locally looks like a line. This might sound like a very weak claim here, right? Because we don't know what does locally mean in this sense. We also don't know what does look like a line mean, right? Doesn't sound very formal. So we will look at it in this plot now. So imagine you have this purple curve in the space. Then what we are saying is that, first of all, locally, right? You can pick any point P. Then I'm going to zoom in by just looking this small region around this point P, which we call U. Then within this small region U, we're saying that it looks like a line. What does look like a line mean? It means I can pick this function gamma P, mapping an interval on the real line AB to the intersection of my curve C and this little region U. So mathematically speaking, we have this definition here, a differentiable curve in Rn, right? We are saying it more generally in Rn. is the set of points C belongs to Rn with a certain property. This property is that for every P of C, there exists an open neighborhood U containing P, and then there exists a smooth function Rp can map an interval AB to the intersection of my curve and this open region. So that I have some further restrictions. For example, I'm saying the first derivative of this Rp cannot be 0. This is try to eliminate the case like the first subtlety we saw before. If the derivative is 0, it means it is a constant, then everything will be mapped into a single point. So we cannot say it locally looks like a line, and locally it's just a single point. But as long as we satisfy this requirement, we have like a valid definition of differentiable curves. And then this function Rp is known as a local parameterization of C at this point P. Okay, now we have defined this term curve in the language of differential geometry. Any questions so far? Okay, then let's move on. The next thing we're going to introduce is so-called parameterized curve. So remember, we say that a curve cannot be a function; it has to be geometrically a set of points. But the problem is that if we want to work with geometrically a set of points, sometimes it can be really hard. So we try to give a more general definition of parameterized curves, saying that well, for sometimes just for convenience, we're going to treat the curve as a function and just work with this function. It makes a lot of derivation easier. And then we can actually prove that for all the curves satisfy the definition from previous page are also parameterized curves, meaning satisfy the definition shown in this page. So here definition 3.2 is saying that a parameterized curve is the image, right, of a differentiable function gamma from AB to Rn. This is like a much simpler language than from previous page, right? It's like consistent with what we learned from calculus. I can just use a differentiable function gamma and then just map a real interval to this Rn space. It can be more general than R2. So in this case, the different coordinates I'm mapping to, I can take them, basically the image of my function, I can take them as my parameterized curve. But also notice here we have this restriction saying that gamma prime of t cannot be 0, meaning we try to avoid the constant case. But other than that, we are good with this parameterized curve. One thing to notice here is this arrow with the green text in the plot saying that now this is okay, meaning for parameterized curves, we can have these interactions of this curve with itself. But for the definition from previous page, a curve, we cannot have this kind of cases. So if we zoom in a little bit, we can see that within this region, right, it can definitely be an image of some parameterized function, right? But it cannot be locally looks like a line, because if I'm choosing this point as my P, and locally I should be able to answer questions like how is this curve changing, right? Because it's a differentiable curve, I can basically take derivatives. So intuitively, you can think of it as if I move a little bit off from this point P, I should precisely know how much my curve is changing. But at this point, if there is this interaction, you have 3 potential directions to change. So at this point, you really cannot tell. But if this is a parameterized curve, right, it is legitimate because your curve might just come this way. And later on, after you change the t value by some amount, it come back from this way. That causes this interaction. But when the first time you pass here, the derivative is along this way. The second time you pass here, the derivative is along this way. Both are like precisely defined. So this makes the parameterized curve a more general definition. So with the parameterized curve, we go back to the previous second subtlety we mentioned. We required its derivative to be non-zero to avoid the first subtlety, but here we still have like the second subtlety of non-one-to-one mapping, right? So basically, this is saying that I can do some sort of change of parameters, and then this change of parameters, basically in terms of two different parameters, may give me the same curve. But when we are talking about some geometric measurements, what we desire for is this invariance. We don't want the change of parameter to affect the geometric property of the curve in any way, right? So to deal with this more precisely, we're going to look at one example of velocity. So velocity here, it's like a property of any parameterized function. If you think of your parameter as the time t and you think of your gamma as the distance you travel, then you can easily compute the velocity by taking the derivative. Here, what we are trying to show is that the velocity, it is not a property of the points on the curve. It depends on the parameterization. Intuitively, this is saying that if I'm driving different cars, right, although along the same curve, I might drive in different speed. This doesn't change the property of the curve, but just because I'm driving in different speed, well, maybe just because I'm driving different cars, it may result to like different velocity. So here, let's do like a very simple derivation. I hope everyone can see the board. Okay, so if you cannot see it clearly, just let me know anytime. We can switch back to the screen share on my iPad, which should be good. So what we are saying is that imagine we have the first parameterization RT in terms of t. Then we have the second parameterization, we call it R tilde in terms of different parameter t tilde. And then what we are saying is that there is this map phi, which takes t tilde and gives you t. So just two parameterizations, we are giving this example such that there is this mapping for you to change parameters. And then for simplicity, we will just assume the derivative of pi is greater than 0, meaning we want this transformation between two parameters to be strictly increasing. So we can avoid that like a non-one-to-one parameter map. But anyway, if we have these two things, right, these are two different parameterizations, then I can rewrite the second one as gamma of phi t tilde, which is further gamma of phi t tilde, right? This is the composition of two functions, and then this is your t. So this equation is saying that, okay, here I have one parameterization, gamma tilde t tilde. I have another parameterization, basically gamma t, but they are the same curve. Then when I try to ask the velocity here, it is simply gamma prime of t versus gamma tilde prime of t tilde.
Shichang?
So here the first prime is
Shichang?
Shichang, can you hear?
Sorry for the interruption.
Yeah.
But could you unshare your slides while you're presenting on the board so that we can pin the whiteboard and see it more clearly?
Sorry, what do you mean?
If you unshare your slides, then we can pin the camera.
Just ask Archie to double click your screen.
Double click my screen?
No. I mean, Archie, you can double click the like the sharing of the whiteboard.
I tried that, but it's still not working.
Yes, but when I double click on it, because the slides are still shared, it doesn't change anything on my screen.
What I did is like I just move the panel, enlarge the whiteboard panel, and then it works quite well for me.
Stop sharing.
Okay.
Yeah, that's even better.
Is it? Because here is one light here, so.
Yes, now I can see it clearly.
but it seems like mirrored to me. Is it?
No, it's fine on my end.
It's fine on your end? Okay.
Yes. Thank you.
Then I will go back to, well, I guess I just need to share and reshare again. Okay, let's do this.
Yep.
Okay, sure. All right, so I have a, okay, is this good? Yeah, thank you for reminding me. I'll try to, because I was not looking at the chat, so I try to make my speaker to the largest volume so you guys can see. Okay, you just speak up if there's any issue. So here, when we're talking about the velocity, it's like for the first parameterization, we can take derivative with respect to t. The second one, we take derivative with respect to t tilde, right? But in this case, we can just apply the chain rule. So what this is saying that I take the derivative with respect to gamma t tilde, but t tilde is just phi t, and then oh, sorry. Oh, sorry, let me use my paper to clean it. This board is a bit hard to clean. But what we are saying is that this is just phi t tilde times phi prime t tilde, right? So this is like saying I have this extra parameter here. So basically the velocity of these things doesn't match.
Sorry, it's hard for me to see. Maybe the writing is too light compared to the background. Like,
okay, wait.
yeah, it's just the R tilde. What's after that R tilde prime is what?
Okay, maybe let's just switch back to my iPad then. Because we try to turn on the light, and then if we turn on the light, you see there is this light on the board, so it's also a bit hard to see.
I think it's because you just erase something. Maybe our board needs to be cleaned. That maybe you can write it just below it because it's just or change to another pen that is darker or something because it just because the mix of things.
Okay. So if I write here, that's good, right? Everyone can see it here. If I just write on the,
this is very clear, yeah.
Okay. So although it for me it makes me feels good when I stand up there, looks like a real mathematician, but maybe it's better for us to use the iPad so we can see what's happening here. I guess this time I'm not well prepared to use the camera. Maybe next time when someone else is doing, they can try the camera. Okay, but basically, okay. Let me quickly rewrite what was on the board there. So we have this gamma t, and then we are trying to say there is another parameterization using gamma tilde t tilde, right? And then for this gamma tilde t tilde, we define it as gamma of phi of t tilde. Okay, this is by definition, we are saying that if we apply this map of different parameters, gamma will take t tilde and give us t. So this, when we put t back to the function of r, we are also, this is also another parameterization of our function, of our curve. Then when I try to ask the question of velocity, so what I can do is I can do gamma tilde prime, which gives me the velocity, right? And then of t tilde, and then this is like I do the prime of just the prime of this thing. So the chain rule. So the outer function times the inner function. Okay, so this is what I get. But remember, as we defined, this is just a t. So what we are saying here, this is gamma prime of t. This is some extra parameter. The second term is some extra parameter. We're saying that the velocity in terms of the first, the velocity in terms of the second parameterization equals the velocity of the first parameterization times some extra factor. So all this wants to say is that we have different parameterizations that leads to different velocity, although it is the same curve. Okay. So in this case, we see that velocity is not something invariant to parameterization, but we can have some other properties that are geometric, so they are invariant to the different parameterization. For example, the arc length. Intuitively, what this is saying is that if I'm driving two different cars in two different speeds, right? I can drive it faster or slower, doesn't matter. But as long as I'm following the same curve, the length of the curve doesn't change, no matter like how I describe this curve, right? So I'm showing what's showing in the middle of the screen is the formula of calculating arc length curve. This is from the calculus class. If some of us are haven't been thinking about this calculus for a long time, the intuition for this is just saying I can take the derivative of t, saying that well within the tiny amount of time, how much do I move? Then if I take the two norm, this is like within this small amount of time, how much distance do I move, right? So this is like a small distance. And then when I take this integral from the point A to point B, this is telling me, okay, from A to B in total, how much distance did I move, okay? So basically this is locally, we try to say our movement are always linear, so we can use the prime to approximate it. When we add this small linear line segments together, this gives me the total arc length. So this is a formula we're going to use. Then let's compute the arc length of our curve, right? Using different parameterizations. In this case, we are saying that we have the first parameter t, which changes from A to B. We have our second parameter t tilde, which changes from A tilde to B tilde. And then again, we have this phi doing this parameter mapping. And then for simplicity, we also assumed phi has positive derivative. Then when we compute the arc length, I use L for the arc length. And then we can compute the arc length regarding the R tilde parameterization. This is A tilde, B tilde. Then just plug it into the formula we saw, right? Okay, so up to this point, I didn't do anything, just to plug it into the formula showing on the slide. Then, as before, we can just take our velocity computation, right? Because we computed this value here, just to plug the result to this integral. So this is what we get. Right, times this dt tilde, okay? And then once we plug it in, we see that, okay, this is just a scalar. We can bring it out of the two norm. So this is what we get. Absolute value d tilde. But if we think about what this is just dt, right? This is like a change of variable. You may see it as dt d tilde equals phi prime of t tilde. Because we assumed it is greater than 0, I can just add absolute value here. But this is just a dt. So when we apply the change of variable of integral, this just gives us back the integral in terms of t rather than t tilde. So this is just this. But this is precisely the formula if we plug in RT in the first place, we started by plugging in RT tilde to the formula, and then we end up with the same formula by plugging RT. So this means these two parameterizations actually give us exactly the same arc lengths. Any questions so far? Okay, so both properties we just saw, I guess they are pretty intuitive in terms of the car driving example. Velocity is not a geometric property, but arc length is a geometric property. Then with this arc length, we can actually ask a question, is there a canonical parameterization that helps us to parameterize our curve? The answer is yes. We can just take advantage of this arc length, saying that if we just use the arc length variable, in this case S, and then we just parameterize it, parameterize our curve in terms of this S, then for every curve, we will have this standard canonical parameterization. So more precisely, what we are saying here is that S can be computed using this arc length formula, which makes it just a function of t, right? Then if I consider the derivative of S, then it just takes what's within the integral out, right? Because it is a norm, so when I'm asking S prime t, this norm is always greater than 0. So if it's always greater than 0, and then this means we can have this inverse function, right? So S before it is a function of t, now we can write it as like an inverse S gives you t, right? No matter what kind of arc length you plug in, you can get back the t parameter. So if we can define the inverse function, then S is just another parameter up to a parameter change. So when we write down the R tilde, like before, we can just use S as the t tilde. So we don't use the t tilde anymore. We are just going to say we will use the arc length as our parameter. So intuitively, what this is saying is that my R tilde S tells me the distance, right? When I start travel from R tilde 0, R tilde S tells me how much I have traveled, the total distance. But if I look at my parameter, my parameter is also S. My parameter is also saying when the total number of distance has changed, then what should the gamma tilde function change? Then in this case, we actually know if we parameterize in terms of S, then the function, the S prime will just be a like a unit length. So basically, this is prime here. So what we are saying is that we are driving a car, and this car should drive with constant speed if we are measuring speed in unit arc length. So we can also visualize this on this plot. So on the left, we're just saying we're just showing like any t we pick, right? When this t change, like any unit change of t may result a different change of arc length. But on the right-hand side, we're showing when we parameterize things using arc length, then with one unit change of arc length, the arc length of output of gamma tilde also change a unit length. So you can see those these areas, they change very uniformly. Okay, so what's showing on the lower right is just formally state what we just said. Right now we define the, remember before we had phi t tilde equals t, and then right now we just change this t tilde to s. We are saying this phi s equals t. Then this phi is just the inverse function of s. If we apply phi and then we apply s inside, this is the identity function. Okay, so now with this nice parameterization, we know for any curve, we can just use its curve length to parameterize it. So we won't get this non-one-to-one problem anymore. And then for the all of the discussion later today, we're going to use this S parameter as our parameterization. Yeah, any questions so far? We're going to move to a new concept now. Okay, good. Now we have defined a curve. We have defined a parameterized curve. We are going to try to come up with some other properties to help us better understand the curve. So the first thing we're going to define is the so-called tangent vector. So basically, the tangent vector is a unit length vector. It tells you at any single point how should like basically what is the tangent direction of your curve. So it's showing on the plot here. At this point, my curve is if I approximate it locally as a line, it is a line changing this way. So I can write out the direction of the tangent vector. And then for the length of the tangent vector, you can either think of it as local change in terms of gamma prime. So from previous page, we saw that gamma prime of S is just a constant 1. Or you can say that when we define the tangent vector, we just think of it as a unit vector. So we only need to know the direction. But in any case, this is how we define this TS. And then I can also write out TS using this coordinate in my mind, right? If I'm thinking about this is the x-axis, this is the y-axis, xy, or I'm saying this is my E1, this is my E2, then by measuring this theta here, I can write t in terms of cosine theta and sine theta. Okay, then the second thing we're going to define is so-called the normal vector. Basically, the normal vector is well, there are also like different ways to come up with it. One way to think about it is we further take derivative of the tangent vector. Basically, we calculate some t prime here. So because the prime of the cosine theta is just a negative sign, the prime of the sine theta is just a cosine. So again, we need to apply the chain rule when we compute the derivative with regard to theta. This is what we get. But other than that, if we compute we still need to compute the derivative of theta with respect to s. So we get this extra factor here. Then once we get this, we can make this observation that 0, 1, negative 1, 0, right? If I take this matrix, multiply it by t, basically cosine and sine, then what I get is negative sine cosine, right? What I get is this t prime here. So in our case, what we're doing is that we call this matrix J, and then we define our normal vector to be this vector, as showing on the left-hand side. But if we further think about this matrix, 0, negative 1, 1, 0, what this matrix does is actually just a notation, a rotation. So basically, it rotates. If we go back to the curve, it rotates my tangent vector by 90 degrees, like counterclockwise. Okay, so another way to think about a normal vector is that we have the tangent direction. We just want to know what is the orthogonal direction. So that's our normal vector. And then for this extra term, theta prime of s, we call it curvature, ks, and we write it here. So the way to think about the curvature is like saying the change of your degree theta here with respect to your parameter s. This is saying that if I'm driving along this curve, right, when I'm driving a unit length, how much should I turn my steer? Like the degree theta, I should turn my steer to stay on the curve, right? So this is the curvature. Also, you can think of it as how curved your curve is. If your curve is very curved, then just driving a small distance, you need to turn your steer a lot. So that gives you a large curvature. So this curvature here, more precisely, we should call it a signed curvature, because back to calculus, when the concept of curvature was introduced, usually people add absolute value on it to indicate just the magnitude rather than its sign. Here we call it signed curvature, but we can always think of it as positive, because it's just up to how you parameterize your curve. If you parameterize it using negative s rather than s, it will change the sign of your curvature. Okay, so now we'll get back to another invariance property we want to talk about. Before we saw that we want our representation to be invariant of different parameterizations. Here we are saying that, can we also make it invariant to different coordinate systems? If we think about the curve in the space, we can use any handy x or y to describe it. But the ideal case would be, this is just some geometric shape, right? No matter what kind of coordinate system I choose, I should be able to describe my curve. So we don't want to go back to any like artificially defined x and y. We want to ask, is there this natural coordinate system for us to describe a curve? And the answer is yes. We can actually describe a curve just using the tangent vector and the normal vector we saw before. The idea is like, we have this curve in the space. Whenever I'm at a point P on this curve, I can compute its tangent, I can compute its normal. Then I have these two directions. Then using these two directions, I can express my shape. I can also tell you some properties of my shape in terms of the derivatives, say the derivative of tangent and the derivative of normal. And then this kind of coordinate system should also be unique, because when you, no matter how you put your curve in the space, you can always pinpoint the point P on the curve and then compute the tangent and normal regarding that point. So so just to summarize this a little bit, so what we're saying is that I can rotate or shift the curve, doesn't matter, but the geometry of it shouldn't change. Whenever we reference back to the Cartesian XY coordinate system, is against this idea of invariance. The problem of like totally get rid of any coordinates is that it makes us hard to understand these measurements, like tangent prime and normal prime. If I can compute the tangent vector for sure, but if there is no coordinate, I'm not sure how much my tangent vector is changing. But once we choose this coordinate system that is intrinsic to the curve itself, the name is Fermat frame. When I choose this Fermat frame, I can have this handy coordinate system that answer what is t prime and what is n prime, just using the t and n basis. So basically the formula showing here, this is what we're going to derive. Okay. So I will just first copy down the formula here. So we try to understand the derivative of our tangent and the normal. Okay, and we are claiming that it can be just categorized using the curvature we saw within this coordinate system defined by t and n. Okay, this is what we're saying, and this is called the Fermat frame. So let's see. Actually, for the first one, for the prime, for the dt ds, this one is easy, right? Because we have already did that on this page. So here, this is t prime is just the dt ds, right? We have shown it when we come up with the definition of normal curve as a normal vector. We have already shown it is equal to the curvature times the normal vector. Here we just put it back to the matrices, saying that it corresponding to the 0ks coordinate of this spaces. So all we need to do is derive the second thing, and then we can also look at here. So the second ns is just negative sine theta e1 plus cosine theta e2. Okay. Ooh. Okay. So ns equals negative sine theta s e1 plus cosine theta s e2, right? And then when I try to come up with its derivative with respect to s, first of all, I need the chain rule. Okay, then this is negative cosine theta s E1, and then minus sine theta s E2, right? But then what is this within the parentheses? This is just a negative TS, right? Because T is cosine theta E sine theta E. So basically we have this negative, so which is equal to negative KS TS. This gives us the formula showing on the top. Okay. All right. What have we done here? So we have this coordinate, natural intrinsic coordinate system to describing a curve using T and N. And then we are saying that under this coordinate system, we can also ask questions like, how does my tangent change? How does my normal vector change? Both just in terms of the curvature under this coordinate system. So this is a really nice property. So let's summarize it a little bit. For any curve, we now have this unit tangent vector TS, which tells us the like how does this curve change? Basically, if we approximate it using a local linear line, and then we also have this new normal vector, also unit vector, which is like you rotate your tangent vector 90 degrees counterclockwise, and then it is perpendicular to your T. Finally, we have a third thing is turning angle theta. This theta measures how much your tangent vector change regarding to a standard x-axis. But if we take the derivative of this theta, it gives you the sine curvature. Basically, this is saying once I change a small unit, the unit in terms of function of the arc length, then this Ks gives me how does my theta change, right? So imagine I'm driving a car along this curve C, then this Ks tells me how much I should turn my steering wheel so the car can stay on the curve. Bring this all together, we get this very nice theorem called the fundamental theorem of the local theory of plane curves. A very long name, but what it is describing is actually very short, very intuitive, like very easy to summarize in one short sentence. It's saying that if I know the curvature, right, then I know my curve. The curvature distinguishes a planar curve up to a rigid motion. So intuitively, what this is saying is that because I have this intrinsic coordinate system, as long as you tell me the curvature of my curve at any point, right, in terms of the parameter s, then I will be able to draw the curve out. I will be able to tell you precisely how does the curve look like. All you need to do is you just change it using some rigid motion. Say you move it to a starting point you like, you rotate it a little bit, but the shape of it is fixed. We can also state it more precisely using this proposition 3.2, is saying that given a differentiable function, meaning the sine curvature, then there exists this curve gamma s from AB to R2 with curvature Ks. If I have two curves with the same curvature, then they are essentially saying the same curve up to rotation and translation. Okay. Any questions about this theorem? Okay. So yeah, this is a nice theorem. We are not going to prove it for now. I have one page of the proof attached in the appendix. We will see whether we can finish all the stuff we have left. If so, we will come back to this proof. Otherwise, you can read the proof on your own. It's not like super difficult. So the next step for us is to move the Fermat frame from 2D to 3D. Imagine before we were talking about the curve, but all we are talking about is its tangent and the normal. both of these two vectors happen within the plane. But when we want to talk more generally, we can actually have curves like go out of the plane, right? Which is like the purple one showing here. It's like a spring. So you have 3 directions your curve can change. So you really need a more complicated system to describe it. In this case, what we do is that we introduce one more vector called the binormal vector. When we define it, we just define it as the cross product of our tangent vector and the normal vector. So when you see is that we have 3 vectors, because by the definition of cross product, right? The cross product will be perpendicular to both T and N in this case. And then we can also apply the formula of the cross product, meaning if I have a T cross N, and then I try to measure its norm, just taking this formula from calculus, we get its length as, I have a square here. Its length will just be the product of the norm of these 2 vectors minus the dot product of these 2 vectors squared, right? In this case, we know T and N, they are both unit vectors, and we know they are perpendicular to each other. So this becomes 1, this becomes 1, this becomes 0. Then that means the norm of this is also 0. Okay, so in this case, we see that we define a new vector, which is perpendicular to the previous 2, and also with unit length. So naturally, we see that all these 3 vectors putting together, they satisfy, they are like they form an orthonormal basis, and then they satisfy a new coordinate system with 3 axes. So we're going to prove something similar as before, like the 2D case. So if we look at this submatrix here, it's just the 2D case. Right now, we are generalizing things to 3D, and then we introduced new terms, tau. Tau here is what we call torsion. By torsion, remember the curvature, we used it to measure the in-plane motion. Torsion here, we're using it to measure the out-plane motion. So let me try to draw something to give you an intuitive idea of what torsion is. So for this part, I have to say that my understanding of torsion is also limited. So if any of you has a better intuition of what is a torsion, just feel free to interrupt me and give the examples to help us here to better understand it. So basically, if we look at a curve within the plane, right, say just like a circle within the plane, then I can draw these 3 vectors I just defined. Say this is my T, this is my N, this is my B. Well, I do have the curvature at each point to tell me how curved my curve is, right? If it's really curved, then the curvature is large. If it's really flat, then the curvature is small. But all the curvature is saying is something within the plane. In this case, the torsion is 0, the tau we just defined, because torsion is really about the out of plane motion. But if I draw another curve, which looks like a bridge in this case, okay, you can imagine it's the same circle. It's like a same circle on this plane. What I did was that I bend this circle, I bend this plane like this. So the circle becomes the picture like on the right. So in this case, I can also maybe say pick a point, then come up with the tangent, and then the normal in this way, and then here the binormal. So remember before in the circle, the binormal on the left is always pointing upward, right? Here on the right, the normal is no longer pointing upward. The normal is pointing like some direction, like towards this way. In this case, we will have a non-zero torsion. Like later we will derive the formula of torsion, but in this case, I'm just comparing 0 versus non-zero. In this case, because I bent the plane, I twisted the plane, then I have a torsion there. So intuitively, my understanding is that curvature tells you how bent your curve is within the plane. Torsion tells you, if I look at things out of the plane, like how twisted the plane itself is. Okay. All right. Now we have defined these two more things. We want to generalize our finite frame from 2D to 3D. Then the formula we will prove is this one. Before we do it, we really need some simple lemma to help us to achieve this goal. So this proposition 3.3 contains two simple statements. The first one is saying that if we have this vector Vt, which is differentiable with unit length, then what I can claim is that I take the dot product of its derivative with itself, then it becomes like a constantly zero. In other words, this is saying my first derivative will be perpendicular to myself if I am unit length. The second one here is saying that if I have two different vectors, then I can actually come up with this identity to describe their relationship with their first derivative. These are the two lemmas we will need to prove the theorem on the previous page. Both of the lemmas are very simple. I should be able to derive them just in this space. So if we think about this Vt square, right? So its unit length, I can just square it. It's still 1. But I can also write it out just as the dot product. Okay. Then what I do is that I take derivative on both sides. So what do I get on the left-hand side? I get v prime of t times vt by vt times v prime of t, just by the product rule. On the right-hand side, I get 0. Okay, so up to here, we're done, right? Because these two are identical. So what I'm saying is that the derivative times itself is like a constant 0. Yeah, this may be something like very simple when you do the derivation, but when you think about it, I feel like there is something profound there, because what we are saying is that for all the unit vectors, its derivative and itself, they should be perpendicular. I'm actually not quite sure whether there is a nice geometric interpretation of this. Yeah, if any of you know it, feel free to speak up. So the second one we try to prove here is also easy. So basically we have two vectors that are perpendicular. Again, we just take the derivative of it on both sides by the product rule. This is what we get: v prime t times wt plus vt times w prime of t. On the right-hand side is still 0, right? But then also up to this point, we're done because the statement we're trying to make here just to move things to the right-hand side. These are the two useful lemmas. With them, we are ready to prove this theorem here. Okay, the finite frame in the 3D case. So let me just copy it here. We now have T, N, B, 3 things. What we are trying to claim is this is K, negative K, 0. Let me see. 0, tau, negative tau, 0, 0. And this is TNB. Sometimes in the literature, this kind of coordinate frame is also referred as the TNB frame. So when you see the TNB frame, you know what they are talking about. Okay, let's do it. So remember, for the upper submatrix, we have already seen it in previous derivation. So right now here, we are just going to derive the other entries. We are going to use our property defined in the, we proved in the lemma. Basically, Okay, let's first say in general, for any V, because these three vectors gives an orthonormal system, for any V, I can write V as V dot product of T times T plus V dot product of N times N plus V dot product of B times B. This is saying I have an orthonormal basis. I have any vector. I can just project my vector on each of these bases to get its coordinate on that basis. Then finally write out this my vector using the linear combination of these three coordinates. Then because this is true for every V, I can just pick V equal to N prime. Okay, this is like a design choice. I choose it to be N prime. Then when I plug things in, I get N prime equals N prime dot T times T plus N prime dot N times N plus N prime dot B times B. When I plug these things in, I can start using the lemma we just proved. Let's make the observation here. The first term, it is N prime of times T. Using my lemma, the second part, I can just write it as T prime times N with a negative T prime times N. Okay, this is the second part of my lemma. I can just negative before it, right? Maybe you can remember it in that way. So then when we look at the second term here, the second term is just N prime times dot product of N. And then this is just a unit length vector. Its derivative dot product with itself. So we know it is 0 by the first part of the lemma. So this term becomes 0. Then we can also look at the third term here. The third term, we can apply a similar thing here. We just change it to negative B prime times N times B. Okay. So yeah, this is just by applying our lemma to all three terms here. Then let's make a further observation. What is T prime? So here, the first entry, we're actually calculating T prime. When we're calculating T prime, we see that it is just okay. Let's continue then. We just keep copying this term around. But why do we do that? Is because this term is how we define our tau. We just give it a name called tau. And then when we define it, we include this negative sign. This is just by convention. You can you can also define tau without the negative, but in order for the following formulas to look better, we just define it with the negative sign. So here we are saying this is our tau. Then we are done here, right? We are done with the second rule because we see we have one term. The first entry is negative k. The last entry is tau. Then it is negative kt plus tau b. Okay, we have proved the second rule here. Let's move on to the third rule for the derivative of the binormal vector. Again, we're going to use the same trick. This time, we're going to pick V equals B prime. So it's exactly the same thing we just plug in B prime to this coordinate system by making projections to each base. Then you will see with those two lemmas, things happen just like magically. Okay, now we plug in B prime. We have 3 terms. For the first one, let's apply the lemma. We get negative T prime times B times T. For the second one, we actually in this case we don't need to change it. We just keep it there. Or we can also just simply write it as negative tau, because we have defined tau here. This is negative tau times n. This one is 0, right? For the same reason, we have B prime dot product with B. Okay, then let's further simplify it. Remember, for the T prime, it is just T prime is just like here. T prime is just k times n, so we have negative T k times n B. So I should say this is dot product, but this is just a single scalar product times T minus tau n. Maybe write it as plus negative tau. Okay. Here, by the definition of binormal vector, it is perpendicular to both the normal and the tangent. So this dot product in the first term is also 0. So it is gone. So all we are left with is negative tau times n. Okay. So you can also see that this matches with our previous definition of tau, because here what we are saying is B prime equals negative tau of n. And then if we also do a dot product on both sides, we get B prime n equals negative tau. So this is how we define tau in the first place. But if we bring it back, to the third rule here, we're saying that, okay, we also get to this 0 negative tau 0 times this coordinate system. All right, has anyone or able to follow along the proof, right? Any questions for me?
I somehow lost attention from between the third line and fourth line. No.
Right here.
Maybe
up.
second to the third. T prime is kn. That is fine.
Okay.
And what is n dot b again? Could you remind how we?
Well, yeah. So yeah, we were going a little bit fast. So this one corresponding to this, and then this one is 0, just because these two things are perpendicular.
Oh, okay, yeah, I got it. Thank you.
Yeah. Any other questions?
Could you show me the formula again?
Okay.
So here, I just want to make sure I understand it well. So when we take the time derivative of n has components both in the direction, the derivative of n has components both in the direction of t and b.
Mm-hmm.
Right, and b has components, derivative of b has components only in the direction of n.
Mm-hmm.
I see. Okay, thank you.
Yeah, so we have done some derivations, right, with those two lemmas we saw. But if we take a step back, what this is saying is very similar to the 2D case. We're saying here, we now have this intrinsic coordinate system described by our tangent vector, normal vector, and binormal vector. And then with these 3 vectors, we're able to describe our curve just using 2 things. One is its curvature, one is this torsion. Actually, there is this nice statement, right? A generalized version of the 2D one, saying that curvature and torsion, these 2 things, they can distinguish any 3D curve up to a rigid motion. Meaning, if you give me the curvature and then you give me the torsion, then I can tell you how the curve looks like. All you need to do to match another curve with the same like curvature and torsion is you need to do some rotation or translation. This is why this TNB frame or the Fourier frame is powerful, because it really satisfies a lot of invariance. This coordinate invariance allow you to like simply describe your curve using just those two quantities. As we discussed, the curve tells you the property, the curvature tells you the property of the curve within the plane, and the torsion tells you the property of the curve when you twist the plane. If I know how the curve behaves within the plane and I know how much I twist the plane, then I know the curve. So yeah, this is basically the last thing I want to say. We do have like one generalized version. I put it in appendix because it's rather a bit complicated. So just to mention this for completeness, we can certainly generalize things to Rn. In this case, we can also ask the derivative. You will see we get two off that, like for both these off diagonal entries. We have something there. They call it chi1 to chi(n minus 1). But basically it's just like extension of the 3D case. Most practical cases only use this 2D curves or 3D curves. So that's why this is the generalized Fourier frame is only stated for completeness.
I never knew about this generalized thing. Oh, this is beautiful.
Yeah, it is very beautiful. I think as I was watching the lecture, the instructor mentioned that he really wants to introduce this one, but he doesn't know any good practical reason for why introducing this one, because he can't come up with example. And then he actually asked if any student can think of like a practical usage of this formula. He would be happy to add that example in future lectures.
Because I waste people's time a little bit, I want to pay back. I wanna, could you go back to the V, size of length of V is equal to 1? And then take the derivative, and then their derivative is the same, is orthogonal. Yeah, that one. I think I have a good intuition actually.
Okay, great.
So here, V, length of V is equal to 1. It means that it is always on the sphere. If it is 2 dimension, it is on circle, 3 dimension sphere, and n dimension is hypersphere, right?
Okay.
So the length is always 1. It's always in unipole, length wall unipole or hypersphere. Okay, so now what it tries to say is that, so whenever, if a particular point is always on the sphere, right? What is the direction, possible direction of the movement? And essentially the claim, the proof is really nothing more than, if I want to stay on hypersphere, then I always move within the tangent plane of the hypersphere. That's essentially what it says.
Within the tangent plane.
Tangent plane, or you can think about it as a circle. If it is a circle, right? The direction of the movement is always like tangent to that circle.
Okay.
So V prime is the direction of the movement, right?
Oh, if I want to stay on the circle. Oh,
yeah,
I
if
see.
you want to stay on the circle, yeah.
Yeah. Okay. Yeah, this is a great intuition. Yeah.
It's a point just to make perfect sense. You don't have to prove anything. It just makes sense.
Right. Yeah. Because we have this restriction saying that it's always unit length.
Right,
so
right.
We have to stay on the circle, so I have to move.
Right. And if it is a sphere, then it is tangent plane.
Okay.
And hypersphere, then hypertangent plane.
Okay. Yeah, makes sense.
Yeah. I hope I paid back.
Thank you for the comment.
Yeah, that's great intuition. I have a question also, like suppose we have a circle, and if we move like clockwise and counterclockwise, we're going to have different curvature. Is that the case?
Yeah, so in this case, we are saying that we have a signed curvature, right? So that's because even though we are using the arc length to, so say we have 2 points A and B, even though we are using the arc length to parameterize our curve, there are always two ways to parameterize it, right? From the arc length from A to B and arc length from B to A. The circle case is just like A and B become the same point. It's like clockwise or counterclockwise. So in both cases, we will get like two different curvatures. They share the magnitude, but their sign are different.
I see. Okay, thank you.
Okay. Any other questions or comments? If no, we have like 6 minutes. I have some appendix slides. These slides, I don't think they fit into the discussion before. Basically, when the professor mentioned this in his video, it's just introducing the terminology. So I will just quickly go through these 3. So the first one is saying sometimes we will also use the term trace, like the image. Maybe when you think of a function, you call it an image, but sometimes we call it a trace when we're talking about parameterized curve. And also when we are looking at 2D or 3D case, this parameterization function, we have these component functions, right? If gamma t is this parameterized function, then 3 component, we just call them component functions. Another thing is the radius of curvature. So this gives another intuition of understanding the curvature. I think this is the first time when I learned the curvature, that's how I understand it. You think of it, how curved your curve is as attaching a circle to this point. So basically, if this curve if the curvature here locally corresponding to this green circle, then I will just use this radius of this green circle to describe the curve. And then the radius of this green circle is actually 1 over the curvature. Of course, in this case, we can think of it as the no sign curvature, basically only the magnitude. And then if it's curved a lot, then I can only attach a smaller circle. In this case, the radius is smaller, but the curvature is larger. So the radius is called radius of curvature. The final thing is what's so-called a Gaussian map. I actually don't see where we use it for the lecture, but just to introduce the terminology. A Gaussian map is saying that if I have a point on my curve, and then because I have the tangent vector, normal vector, binormal vector, I can define this map from any point just to its normal vector. So let me state it again. It's like I have a point here, and then I can compute its normal vector, looks like this, a unit length vector. And then I just define this map to be from the point itself to the normal vector. They say that Gaussian map is a map from any curve to the unit circle, because in this case, the normal vectors are all unit lengths, just pointing to different directions. Maybe this will become useful later when we see surfaces or more complicated geometries, but I just want to tell you what does Gaussian map mean in this case. Okay, that concludes all what I want to say, including the appendix. These are the references I used. I mainly focused the shape analysis course because I feel like it is a superset for the other Stanford course. If you were reading the slide of the Stanford course, I encouraged you to read the shape analysis as well because it has more content here. Any final questions for me? If no, I think we are good to go. Thank you for everyone here.
Thank you, Shichang.